Okay, so thank you for giving me the opportunity to present my work twice. So first I introduce myself. I'm Marco Pelegatti and I work at the University of Udine. So in this presentation I would like to discuss the results that we obtain about the cyclic elastoplastic response of a lattice structure produced by additive manufacturing, which is a type of behavior not frequently reported in literature. So I think it's best to first define the goal of the study, which is to describe the mechanical response of a lattice structure subjected to low cycle fatigue loading. In particular, one of the aims is to model the cyclic elastoplastic response. So in order to achieve this goal, we must perform some low cycle fatigue tests on lattice specimen and then model the experimental behavior. So here I illustrate the timeline of the study, which is an ongoing project. Until now, we carry out some low cycle fatigue tests on the bulk material in order to model its mechanical behavior. Then we perform some finite element simulations to understand the cyclic response of the lattice structure. And finally, we draw the specimen geometry based on these simulations, the literature, and one experimental test. So the next step is to manufacture the specimen and test them. This is the outline of my presentation, which mirrors more or less what I already discussed in the timeline. So firstly, I describe the finite element simulations on a unit cell, and then in the second part, I'll discuss the results obtained by testing a lattice structure. So now I'm going to present the main aspects of the finite element model of a unit cell. The geometry of the unit cell is an FBCCZ with a relative density of 51%. This kind of structure was already manufactured at the University of Udine for another project in the past. And as I said in the introduction, the technology used to manufacture the specimen is the laser power bed fusion, which is an additive manufacturing technique. So regarding the finite element model, the material considered in the simulations is a laser power bed fusion 360L steel that we tested in low cycle fatigue condition, and then we model its cyclic behavior with Chabosh and Voss models. Actually, we simulated the response of only 1/8 of the cell to reduce the computational cost, since one of our goals is to find a fast and accurate way to model the cyclic behavior up to the stabilized state, which is computational demanding. Then, of course, we imposed a cyclic displacement and used the periodic boundary condition. Here, as an example, I present a comparison between the simulated response of the bulk material and the unit cell for an imposed macroscopic strain of 0.7% for 700 cycles. So without going into detail, both the stress strain cycles and the cyclic stress response showed that the unit cells has a similar cyclic behavior compared to the bulk material, with some small variations. So at this point, I'd like to present the results obtained by testing one of the lattice specimen that I showed you before. This is the experimental setup, basically the same one used for the bulk specimens. We carry out a standard low cycle fatigue test imposing a 0.7% of strain amplitude under symmetric tension compression. And as you can see, the specimen failed near the middle zone. Concerning the experimental results, here on the right I reported the stress strain cycles for both the bulk and lattice specimens. If we compare this data to the simulated behavior, which I reported on the left, the lattice structure response is quite similar. Despite this strong similarity, if we give a better look, the simulation using a single unit cells gives a significant error respect to the experimental data. So to improve the simulated response, we decided to model the response of the lattice structure with lower degree of approximations, but of course an higher computational cost. So basically we simulated the response of a full section of the structure with 16 cells. For example, in the case number 4, we also modeled the struts with full diameter at the boundaries, and as you can see, the macroscopic response is much closer to the experimental data, but the best results were obtained including the dimensional errors in the model introduced by the manufacturing process, which is the case number 5. So just to explain what I mean by dimensional errors, in brief, we observed that the inclined struts had almost an elliptical section, and the dimension in one of the axes was bigger than the nominal diameter. So we measured this deviation and then we made an approximated correction. So basically we maintain the circular section and we calculate an equivalent diameter based on that error. With that adjustment, we also carry out a cyclic simulation of the structure, and as you can see, the cycles are well represented despite some small deviation in the last cycles due to the onset of the fracture. So before I conclude, I present the specimen geometry that we plan to produce. Well, in this moment we already produced this specimen. The geometry is similar to the one that we tested, but based on the results obtained, we choose an higher number of cells in the section to reduce the influence of the boundary effects, though the difference between experimental and simulated response is mainly due to the dimensional errors. And yes, we made also some other small changes to improve the experimental setup. So now I conclude my presentation with a summary. We can say that Chabosh and Voss models are suitable to represent the cyclic elastoplastic response of the bulk material and the lattice structure. Concerning the low cycle fatigue test on the lattice structure, the response of the unit cells becomes representative, increasing the number of cells in the section. And then the best results are obtained if we include also the dimensional errors in the finite element model. So with that, I conclude my presentation and thank you again.